Hi, my name is Energy. You can call me G. I'd like to learn risk engineering. Can you help me with that?
Yes, G, I'm sure I can help you with that. We're going to talk about power transformers today. We're going to learn about what they are. We're going to learn about what the risk issues are, how to manage the risks, and then, we're going to tell some stories. So let's get into it. What are power transformers? They're basically equipment that converts electricity. Generally, we're converting voltages, and the primary purposes that we see power transformers used in the energy industry, specifically in the power generation industry, they can either be used as generator step-up transformers, or they can be used as transmission and distribution transformers. And there's a difference, and we'll get into some of the differences in operations later. But the equipment, it's full of electricity, and it's generally full of oil. Sometimes the oil is less flammable. What that means is that the oil will, if it's on fire, it will go out all by itself if you don't keep a fire touching the fuel. So it's a piloted ignition. If you have something that will keep it going, it will continue to burn. But if it just spills out on the ground, it'll go out by itself. So there's some risk benefits to the less flammable fluids. And then they're full of hundreds of gallons to tens of thousands. 30,000 gallons of mineral oil right there in the middle of your plant. To top it off, they are a bottleneck. Generally, they're not installed as spares. There's some renewable projects that will do that. And we might see 250% capacity units installed to meet the entire demand, so that if they lose one or the other transformer, they don't lose the whole site. That's an option. Then the lead time is forever, basically. Anywhere from 12 to 24 months, depending on the size of the transformer. And you can cut that down by being ready for it. We can talk about contingency planning, but basically being ready for the day that the transformer fails. And I just love the answer. Whenever you ask your T&D folks, your operations folks, when do you plan to replace the transformers? And they'll tell you when they fail. So they're going to fail. It's a matter of time. It's not a matter of if, right? So let's look at what are the risks? Why are we concerned with these transformers? Well, besides being a bottleneck and besides being very expensive and a long lead time items, they are critical to deliver our product, right? So even if it's not a GSU, if it's a power transformer in a refinery, you need that for your process, right? So typically all the transformers we have are very critical and very important. And why do they fail? It's pretty simple, and this is something that everybody can keep with them from now on. Transformers fail because the insulation breaks down. Pretty easy. What's the insulation? It's paper and oil. How does it break down? Overload it, overheat it, or get it wet. Okay? So if we can just manage those simple things, we can protect our transformers. Still need to look at end of life because they won't last forever, even though there's some out there that are 60, 70, 80 years old and still operating. All right, what are the risks? A transformer failure is, it doesn't happen every day, but for those in heavy industry, you're probably familiar with transformer failures because, like I said, they're not really replaced until they do fail. So if they have been replaced before they fail, very good for you, whoever did that. Leave me a comment. I'd like to know who it was. And then, the very small percentage of the failures actually turn to fires. But when they do, it's catastrophic, and it can take out more than one transformer. I'm going to tell you a story later about a station service transformer fire that almost took down the entire plant. The way it burned. There were deluge systems on the switchyard transformers that protected them, and I'm going to show you those lessons learned. But the turbine building itself just took a direct hit from the oil that was right up against it, and you'll see some of the photos from that. They're pretty impressive. But what we learned there was that the deluge system spread the oil. They ran for 3.5 hours while this fire burned. The fire department was terrified to shut off the sprinklers, right? right? They're all trained in their fire academies across the country and across the world. Do not turn off the sprinkler. So they didn't. They let the water run for 3.5 hours. We'll talk about that fire later. But the point is that the deluge systems are not there to put the fire out. They're there to protect the surrounding equipment. And sometimes that helps, if you understand that, it helps with the design and what your intent is. You have to be really careful about runoff. Sometimes the runoff from a deluge system after a fire or after a release of oil, the runoff can cost more to clean up than the actual transformer was worth, or even the downtime is going to cost. So we want to be careful about that. All right. So when do you replace a transformer? This is the big question. I did have an occasion when I was with a utility where we had a 60-year-old transformer. Actually, we had a bank of 60-year-old transformers, and they supplied a major metropolitan area, all the banks, all the tourist areas, all the hotels, apartment buildings, all the downtown area were serviced through this substation. Now, the substation had 3 different circuits, 3 redundant circuits coming into the station, but the 3 transformers that fed the load, and then they had an installed spare. So they had four transformers side by side over a common dike, and if any one of those failed and caught on fire, they had a manual deluge system that was basically valved with 2 valves. So you open up one valve and it puts water on these 2 transformers. You open up the other valve and it would put water on those 2 transformers. If either of the middle 2 transformers were on fire, you really needed to open both valves, but there wasn't enough water supply to do that. So in this case, we ended up replacing those 4 transformers with one new 3-phase transformer that was modern and outfitted with all the instrumentation. So it was a matter of managing the risk. And when we asked the question, when are you going to replace it? And they said, when it fails. We said, well, this is what a failure will look like with this downtown metropolis without power. And how long did you say you were going to be down? Then they start thinking about what the consequences are and the fact that this whole discussion is out and that they've either got to do something or cross their fingers that we never have a blackout downtown. Now, should you have spares? This is a tough question, and it always boils down to what is the spare worth in terms of risk reduction and what is the spare cost. And I will put together a video on analyzing recommendations and prioritizing them based on cost of risk and the cost of risk reduction, and then on what the cost to implement the recommendation is. But basically, it's a case-by-case basis, and we've seen occasions where a utility could buy one spare, outfit it with a load tap changer so that its low side voltage could be changed to match whichever generator happened to need the new GSU or the replacement GSU. So this one transformer was backing up 4 different transformers on their system. So in that case, it made sense to do it. In other cases, say again, if depending on your contracts and what you're required to produce, it may be beneficial to have a spare transformer ready to go in case you have one fail. Let me say that if you have spare transformers, they need to be maintained. We've also had clients that had spare transformers and, within basically days of installing the spare transformer, it fails. So it's really important that the spares are maintained equally as vigorously as the main operational units are. And then we're going to look at, are there exposures? Because the risk isn't just to the transformer itself. A lot of times, especially with GSUs, they're going to be up against the turbine building or up against a switchgear building. So there's going to be exposures, things that could be damaged by this transformer. There could be other transformers being exposed by this transformer. And so once we start getting into exposures, we'll look at firewalls. And we'll talk about firewalls, and there's some alternatives. When I first got into business, a firewall was basically $1 million. And they had to have horrendous footers to keep the wind loads from blowing them over. So in substations, digging deeply around transformers is difficult. We found a couple of alternatives, and perhaps that's another idea for another great video, just one all on firewalls. Believe me, we've got it down to just 100,000. Believe it or not, we even have one way to get a firewall in there, say a 16 by 20 firewall in 4 pieces for $20,000. And it's made out of concrete, and it's, you know, a foot thick at the bottom, 8 inches thick at the top. It'll stop a fire, and it'll stop a blast. So there's alternatives that don't have to cost $1 million. We'll put a whole video out on that. Yeah, you like that one, huh? All right. So how do we manage the risks? What are we looking for? How do we anticipate the things that could go wrong? Remember, I said that the reason transformers fail is that the insulation breaks down. So that's a clue. If we can kind of just keep up with the insulation, that's going to really help maintain the life of the transformer. Some other things that we want to do is keep it cool, right? We have cooling systems, and these cooling systems have fans. They sometimes have pumps. So, we need to maintain the pumps and fans. If you have a oil pump on the bottom of a transformer trying to push the oil, if you shear a shaft on that and you're not checking the starting current on your motors, you'll have no idea why you're not getting circulation, or that the circulation is only basically natural gravity circulation. You're not getting the boost of the pumps because that shaft has been sheared. If you're not checking periodically, how would you know? So online gas monitoring. The gas monitoring, you have to remember, dissolved gas analysis is after something is already going wrong. In fact, half of the transformer failures have good DGA results. Let me say that again. Half of the failures that you find where the transformer died, if you go back and look at the previous dissolved gas analysis reports, they were fine. There was nothing in the DGA report that would have indicated that a failure was about to happen. So if DGA is missing half of the failures, what else is there? What else can we do? Partial discharge monitoring is a alternative, and I'm going to get deep into that. We had a request that I get a little deeper into some of these subjects, so I'll keep it high for some of the brand new beginning risk engineers, and I'll get down into the weeds for those of you out there who want to get deep, because we can get deep. So online gas monitoring is just another form of DGA, dissolved gas analysis. When I see these monitors on the transformers in the field, they're rarely connected and they rarely work. And if they are working, they're not really giving any information. There might be a alarm that goes to a general alarm, and then someone has to go out and look at that device, maybe download the data to figure out if there's a trend in one of the gases. So they're nice and they can be a great thing, but I haven't seen the implementation really pay off yet on those. Still waiting for that. Vibration is something that we can measure in transformers. They're generally, they don't have moving parts, so you shouldn't have vibration. However, as the old joke goes, why does a transformer hum? Because it doesn't know the words. Well, if it's humming, that's vibration. And we can measure that vibration. And if the vibration changes, then, we've got a reason to suspect something's happened to the machine. And typically you just go out and it's the same vibration. Nothing happened. But one day, big steel company out on the system has a ground fault and your plant trips offline, your transformer protects the plant, you get off, the breaker's open, and now you decide, well, did something happen? We could do sweep frequency response analysis, and SFRA. That's a technique to basically, they inject a signal, they look for a reflection of that signal and see if it comes back the same way it went in. If it didn't, they know that they've got a problem at that frequency. Anyway, they've got a way they can look into it, but that can cost a little bit of money and it can take a little bit of time. Another way is just put a vibration probe on the transformer. Did the vibrations change after that massive trip? And, if nothing changed, nothing changed. But if something changed, it clues you in to do some of these other things. Like later, we'll talk about partial discharge. Now, how do we manage these risks? Well, it's one thing to uncover them, observe them, and see what's happening with all of our diagnostics, but how do we actually affect whether we're wearing out the transformers or not? Well, the kind of things that will wear out electrical equipment are rapid starts and stops, cycling, or overloading it or undercooling it. Okay, so when would we cycle? You would cycle if you were in a situation where you were providing the GSU for a power plant that cycled. So that transformer has to match whatever that plant is doing. And that can be a solar plant. Every time a cloud goes past the solar plant, the output goes down and then it goes back up when the cloud goes away. That GSU is responding to that, in real time. It has to make up the voltage difference to stay on the grid, and what it's going to do is it's going to start to accumulate heat in each one of these cycles. So the other kind of area where we start to see cycling, or we actually see no cycling but potentially overloading, is out on the system, the transmission distribution system. Typically those transformers can't be overloaded because, they can be overloaded. The T&D are the ones that are susceptible because the power can come from many plants and go to many loads. So it's easy to have a bottleneck and overload a T&D transformer. A GSU is very unlikely to be overloaded because it's sized for the generator it's hooked to, right? In the original design, they make sure that this generator matches this GSU. And you're probably not overloading your GSU. Now you can undercool it, and that can cause it to fail. I'll talk about a loss at the end of the presentation about water getting into a transformer, and basically how that water hid for a long time from the DGA reports, and no one knew that there was water in the transformer before it was too late. So we'll talk about what the impact is of having to respond to renewable energy. So when big baseload plants were built in the past, they basically had the right to be dispatched first so that they could make back the capital to pay the stockholders that built the plant. Remember, the ratepayers don't pay for the plant until it's actually making power. So the stockholders take the risk that it'll get built and that it'll actually make money, but they don't get to make any money until they get online. So it's important that they get back up online. Now, installed spares, if you have that, wonderful. And like I said, in this one substation that, we had a three-phase bank, we had an installed spare. Even 60 years ago, they realized that that was a critical substation and that there better be some redundancy and reliability if you were supplying a downtown metropolis, right? All right, so if you have installed spares, it's probably going to be maybe two smaller units, two 60s, but not likely to have two 100% capacity transformers, just one sitting there not doing anything. Now, how do we manage the life of these transformers? Because, eventually they do need to be replaced, and we really can't just wait until they fail to have the insurance company buy us a new one. A lot of insurance companies, or let me say, some insurance companies are putting limits on how old of a transformer they'll insure. So we can't go on forever just getting 60, 70, 80-year-old pieces of equipment insured for replacement value without some sort of change in underwriting. So I do feel bad for the underwriters. That it's one of the most frequent losses, and their guys are looking at these things all the time. And like I said before, half of the failures come from transformers that had good DGAs. Well, they're not doing the rest of this stuff. They're not doing the PDA. They're not doing IR. They're not looking at the inrush current on the oil pump. So there's a lot that could be done to manage transformer health, but you still have a time when it has to be replaced. So how do you make that decision? Well, it's going to be a lot of money, so maybe the way we allocate capital is a good place to start. And we can say, well, okay, how old is the transformer? Have we gotten its useful life out of it? And is it in a service that is it a cycling service? Maybe it's not that old, but it's cycled and it's worn out. Maybe it's not that old and it's overloaded and it's worn out. So its service is important. The condition, has it had some trips? Has it had any kind of challenges to its internal core based on ground faults or system phase-to-phase faults? Anything happened that could impact the internal condition or cause known issues with that transformer. And then you have to get into what does it cost if I take this transformer out of service today before it fails. I might be able to just rewind it and get some value out of it, right? Rather than waiting for it to fail and then just having the scrap value of the metal. So getting this plan of when you repair, if you do it before you need to, it's going to serve you in the long run. You might end up with a spare out of that. And then that's risk management that you can't really, you can't buy, right? An insurance company can only give you money. They can't give you the transformer that you need to get back up and online when you need it. But if you've got it sitting there running, there's no deductions on it, there's no deductibles, there's no limits, it's yours. You get to use it and it manages your risk. So think about taking some of your transformers out of service that are way old, especially the ones that are headaches, the ones that you're having to do a lot of maintenance on now, the ones that aren't reliable. Have a plan, have a way to phase these out and make sure that you keep the reliability for the system. All right, now let's talk a little bit about this, the dissolved gas and some of these tests that I mentioned earlier. DGA, I'm not going to make this a video about understanding dissolved gas analysis. There's plenty of those out there, and I'll just say this, that, you know, as a risk engineer, there are plenty of places for you to look and get the details, but when you get a DGA report at a plant, you're going to want to look at the comment section. You want to look at the condition of the equipment, of the transformer. Is it a 1, 2, 3, or 4? And are there any recommendations for testing, retesting before the next year or before the next 6 months? Whatever the frequency that test is being done on, you're looking to see, do they suggest or recommend something sooner, like test it again in a month or test it again in a week? So these are the kind of things that you need to look at when you're looking at a DGA report. You don't need to know that acetylene is bad and you don't want acetylene, okay? When you get into risk engineering, you'll get that. No acetylene. Hydrogen, okay, might be some, you know, arcing going on. You're not going to need to know what gas is attributed to what fault, because remember, the only things that mess up a transformer are arcing, right? Or losing the insulation, right? That leads to arcing and overheating because the insulation's failed. So we're going to look for those things. Now, when you have half of the transformers fail with good DGAs, any kind of test that is only 50% at telling you that you have a problem, and then those 50%, it doesn't even tell you when to shut down. It just tells you it's time to test again next month. And then if it really gets bad, test again next week. And if it's really, really bad, they test every day. I can't believe how long companies will test a transformer that's in the middle of a failure. It's like they're watching a slow motion explosion. It's going to happen, right? Dissolved gas analysis helps, but don't rely on it as the only thing to tell you if your transformers are good or not. So, partial discharge analysis, I'll get into that a little bit deeper. I told you a little bit about sweep frequency. We need to look at the oil condition, and that's more the physical factors of the oil, not so much if there is dissolved gases in the oil, but is the oil still provided, is it still anti-corrosive? Does it have its fundamental properties as a heat transfer agent in the machine? And then the paper condition. Remember, we have oil insulation and we have paper insulation. You can tell how old the paper is or how weak the paper is basically by getting a piece of it and pulling it, right? So there's special tests where you can go in there and take a clipping of the paper and determine really how much life is left in the transformer. We'll talk about moisture. Now, oil floats on water, right? So you can have a big transformer with 30,000 gallons of oil, and there can be a couple of inches of water on the floor or on the bottom of that transformer. It won't really affect anything if it's not up in the core. Now, the lesson we'll talk about later is what happens if the moisture comes in from the top. Stay tuned, you'll see about that one. All right, now what is DGA? Like I said, 50% of the DGA of the transformers that fail had good DGAs. said that before. It's slow to catch issues, right? It's slow because the frequency that we're looking at the test results are once a year, once every 6 months, once a quarter. It's a long time. Even online monitoring, if it has an alarm, you're not even looking at it once a year. You're waiting for the alarm to come in. So it's definitely a slow way to catch a transformer problem. And then, like I said, the typical action is just to retest. It's just to go back out, take another sample, and do it again. What I've learned from my experience in understanding dissolved gas analysis reports is that you have to look at trends. And that's going to be the main thing that you'll see, especially when something is slow moving like this. You have to try and observe trends, and you're going to look for the trends in things that indicate overheating, and you'll learn that it's going to be the ratio of the CO2 and the CO, and you can kind of watch that ratio and figure out if oh, well, maybe we have a fan that was replaced and they put it on backwards. And that's happened, folks. We've seen, the cooling fans basically going backwards on a transformer, not doing its thing. Well, when you fix that, flip it back around, or say there was a temperature switch that was supposed to start the fans, it wasn't working. So this CO2 ratio goes up. You see something's causing the oil to get hot. What do we do? What is it? Oh, we go check the cooling systems. Are we getting cooling? Well, then we find out that switch is bad. We fix it, and then you start trending and you see, oh, it's leveled out. There it goes. So now we found it. And that's important too, because you don't need to degas. You don't need to hide your problems. You just need to understand what they are. It's okay to have that ratio and then have it locked in there, and then that's the future baseline. And you're going to watch and make sure that nothing goes up from there. So that's the way you would use DGA. Trending's important. Looking at your CO2 ratios. Arcing kind of tells you that there, if you've got acetylene or hydrogen, then you've got some kind of arcing. But any dissolved gas in your oil tells you that you've already got something happening in that transformer. So, to the rescue, partial discharge analysis. It's been used in the generators for a long time, and I met a great guy, John Glessick. He used to work for a big utility in Illinois, and he was in charge of all the substations, and he found a great way to apply partial discharge analysis to the transformers. So hopefully I can tell you his story. But basically, the idea of partial discharge is that when you have a sine wave, and I'll show you another graph that shows it, but at the top of that sine wave and at the bottom of that sine wave are the peak voltages, right? And right at those peak voltages, if the insulation's not perfect, you might leak a little bit. So that perfect sine wave might look like a little squiggle at the top and a little squiggle at the bottom. We'll show you what those squiggles are. That's partial discharge. And now, if we can just capture that on a scope and see what it looks like and figure out where it's going, then maybe we can do something. The really neat thing about partial discharge, and you'll see better on the graphs, is that when one partial discharge peak ends, and then that next partial discharge peak starts, that time difference is what tells you whether to leave that transformer in service or not. Okay? Unlike DGA, which says just test it again, partial discharge analysis says you're good to go, take it out of service. One day, this is the number you have to do. If it gets to this number, take it out of service. Today it's not at that number, you're good. And you can go walk up to the machine. You don't have to sample the oil and send it to a lab and find out if the partial discharge is good or not. You can walk up to the machine with a piece of test gear and find out if the partial discharge is growing or if it's not. So,
John, as an experienced underwriter, I must say your stories are so engaging and educational. Keep up the great work.
Will do, Lee. Thank you. So now let's talk about understanding the transformer, right? It's two coils, and basically we're taking a high voltage and we're trying to convert it to a low voltage, or vice versa. If it's a GSU, we're trying to convert the 23,000 volts in the generator up to the transmission voltage of potentially 500,000 volts. So what's it look like when we have a little bit of PD going on? And I'll show you on the curve, but just imagine for a second that, within this set of coils, we've got something buzzing down there. And what happens next is that it creates an electromagnetic pulse. If you're walking out there with an AM radio, you'd hear static, okay? So where does that go? It touches the side of the tank, and then it goes through the side of the tank to ground. So we've got something going on with EMP that if we hook up a coupler, basically a magnetic coupling on that ground clamp, we can read the EMP going through it while the transformer's in service, full load, full power. So then the machine, basically analyzes the information and gives us a great readout that we can figure out, do we have partial discharge? Is it a problem? Is it about to cause a failure? This picture just shows you what partial discharge looks like. It's lab created partial discharge, but what starts to happen before the arcing, you see all that black coloration. That's carbonization, and it's growing across a piece of paper, and it's very conductive. It's ready to conduct electricity, and this is the state that it's partial. But when it goes to full discharge, that's when the arc happens. Okay, so let's talk about what that looks like a little bit. And again, like I said, that we've got a little bit of discharge at the peaks of each of these waves. So at the top of the first peak and the bottom of the second. And if you look, there's 7 milliseconds, right? And so we get a little bit of discharge, and this is what we call small partial discharge, and you wouldn't really take any action for this. Now, you go back out and you measure it and you see that it's only 2 milliseconds. Well, you can see what's happening here is that we're getting closer and closer to continuous discharge. 100%, the whole sine wave filled up with discharge means the voltage is leaking. We don't have a solid circuit anymore. And that's when we have the complete arc. Okay, so that's the beauty of partial discharge, is that you get this number and you decide what to do with it here and today. You don't have to wait and wonder, what should I do? And you don't have to ask yourself the question, why did my transformer fail when I had good DGA? And I'll talk to you about a plant that had good DGA, no moisture, and it failed, and partial discharge could have helped us prevent that. So once we have the failure, we can have a fire, and we got to manage the fire. The fire in, again, the transformers, basically the transformer's dead, it's gone, and what we're trying to do is to keep that fire that's in the middle of the plant from causing too much more damage. We do that with firewalls, deluge systems, we have drainage control, we have dikes, we have whatever we need to keep that oil in place, and especially if we start putting water on it, deluge systems, you're going to spread that oil a long way, even over gravel. I'll show you some pictures from a fire that experienced before. So here's a fire occurring, and yeah, you've probably already seen it on the internet. But what we're going to do is, I'll let you watch this for a second. The oil is boiling, and it's releasing. Now it comes out of a relief valve and ignites, and that's that. That's a lot of oil. So transformer fires can be very devastating. We don't want them to happen. We do what we can to prevent them. Again, firewalls, I'll make another whole video on firewalls, because that's one that I think everybody will benefit from, whether it's power gen or refineries. Here we go. This is what can happen, and this happened at a site that when I was working in a utility, and you can see that left picture, basically the corner of that station service transformer just ripped open from the pressure of the fault. Now that corner was, if you look in that right picture, the corner that you're seeing is in the back side. It's back there where those 4 guys are with the hard hats. And what happened was all the oil just sprayed out of the transformer right up against the turbine building. And they fought that fire for about 3.5 hours. When the fire department got there, They had 55 firefighters show up for this fire. It was in a metropolitan area. It was at a power plant, and it was roaring. All the deluge systems were running, and they just let them run, and the fire spread. And they realized that it was just going to continue to spread until that oil burned out, and it was starting to go through the windows of the turbine building. So they put their firefighters in the turbine building spraying water. 55 firefighters trying to keep this fire from getting into the turbine building, when all they had to do was shut off the deluge system and put down a few gallons of high expansion or of low expansion foam, just a little bit of AFFF, and the fire's out, and within 15 minutes of them getting there. But they're not trained well enough in that kind of firefighting, and I will admit that their training is don't shut off the protection. So this fire, you can see that we had deluge, and look closely at the picture on the left. You see that most of that transformer is protected, but guess where the water spray didn't cover? You see that little cabinet, it got scorched. We opened the cabinet up, all the wire in that was melted, but the rest of the transformer was fine. The little box to the right of the melted box was within the envelope of the water spray, and it was protected. On the picture on the right, you see the conservator tank has a black spot, right? Well, it was okay. The bladder got replaced, and this transformer did survive because of its deluge system, but you can see that we need another head there, at least on this side, probably one on the other side. So it's a good chance to redesign your system after a fire. Make sure that it's going to cover everything that you need covered. Like I said, the fire was so hot, so big. This is the top of the turbine building, and you can see that it was going up into the roof. Had it got up into the roof, I think we would have lost the whole plant. There was really nothing to stop it. These firefighters weren't industrial, and there was nothing in the way of fixed systems that was going to stop a roof fire from rolling right across all the units. So, what happens to a transformer when rain falls on it for 50 years? Well, if the transformer top is pitched to drain, no big deal. But if the top is flat and level, rain can accumulate. And if you have equipment on top of the transformer that prevents you from inspecting it, then you may not notice that puddles are forming. And those puddles could rust out the welded seam on the top of that tank. Now, rainwater would slowly drip in from the top of the transformer. If water droplets come into that transformer and they hit that core, the core is copper wrapped with paper. Well, that paper has a better attraction to water than it does to oil. And what happens is the water goes in there and just goes into the paper, and then any oil that was in the paper gets pushed out. So it's kind of like a backward sponge. The more water that goes in it, the less oil it can hold. Well, you don't see a problem with your dissolved gas analysis because the water is not in the oil, it's in the paper. So you never see a moisture increase in there. And, what is going on? Well, as the water replaces the oil in the paper, the insulating ability of oil and paper is much better than the insulating ability of water and paper, right? So as we become more like water, eventually we have no insulating ability and we get a fault. Fortunately for the site that we had down there, we didn't have an explosion or a fire, but we did have a fault. It was a challenging insurance claim, one that started off a little shaky because it had to do with overtime and corrosion and all that, but it ended up getting paid, and that was...
Thanks for the great stories, John. You make energy risk engineering so easy to understand.
Well, thank you. And Dee, Miss PSM Manager, it's great to have all of you folks who are just trying to come up to speed on risk engineering and learn about it. Learn with me. I learn every day, and I'm going to keep making these videos, keep liking them, keep giving me comments. Love doing them. Thanks a lot.